Alright, so this is our week 12 tutorial. So the first question is simple. It is infinite potential wave problem. So or in other terms, particle in a box kind of a problem. So the wave function is given like this, and here A represents the side of the box. Toward here you can see you are familiar with the wave function already, and you are familiar with the potential as well. And it is said that the which one of the statements out of these four options best describes such a particle in a box problem. So one is saying that how many number of nodes are there for psi and x. Then second is a wave function corresponding to different energy levels are orthogonal. So that you already know that that will be correct, because you know that different energy level correspond to eigenfunctions which are orthogonal, because that is the basic property of this kind of eigenfunctions. Okay, and then number C, some energy levels are degenerate. So for a 1D particle in a box problem, there is no degeneracy, so this will be false. And the fourth number is the energy between adjacent levels is constant, which is also false, because you see that the so let me write down here only, because you know you are already familiar with this 1D particle in a box problem from earlier lecture, so I will not show the derivation to you anymore, but I'll just write down directly the energy eigenvalue formula, which is n square pi square h cut square by 2m a square, where the energy levels go as n equal to 1, 2, 3, etc. So the lowest level is n equal to 1, then n equal to 2, etc. So here the energy level differences between two energy levels, let's say between n equal to 1 and n equal to 2, the delta E. So because here you can see that the En goes as the quantum number n squared. So delta E for n equal to 2 to 1, this difference is 2 squared minus 1 squared times some constant which is pi square h cut square by 2m a square, which I let's say call as E naught. So this is basically 4 minus 1, which is 3 E naught. So the difference is 3 E naught. But for n equal to 2 and n equal to 3, you see that then delta E equal to 3 squared minus 2 squared times E naught, which is 9 minus 4 or 5 E naught. That means you see that from level to level this difference is not constant, but that is varied. So this is false. The energy levels are degenerate. That is also not true, because this energy is only true for a particular one value of n. Then for another value of n there is a different energy value. So none of them are degenerate, because this is a 1D box problem. If it was a problem of a 2D or 3D particle in a box, then you would have the option for degeneracy, because then you had to choose from the linear combination of n1 square and n2 square up to as a total of n square. So based on the combination of n1 and n2, there could have a degeneracy, but here there is no case like that. So degeneracy is also false. Now the wave function for different energy levels are orthogonal is true, because you see that this wave function is represented as sine n by x by a. So for a different energy level, just this n value will be different. So let's say for n equal to 1, you have sine pi x by a. Then n equal to 2, you have sine 2 pi x by a. So if you have this kind of a psi n, so you have sine m by x by a, sine n by x by a, and when you integrate it under this whole x from minus a to plus a, you will see that the value will be 0 for m not equal to n. Okay, and the value will be 1 for m equal to n, because that is the property that it will be normalized. So normalized means psi n this kind of a inner product will be 1, but because of orthogonality, so this psi n for n not equal to n will be 0. So this is the also a property of this wave function. So this is true, but the first one was that whether psi n x has n minus 1 nodes. So what do you mean by nodes? So by nodes I mean to say that how many number of times it actually cuts the x-axis, where the y-axis or wave function value goes to 0, except for at the edges. So like say at the edges it will be anyway 0, because the box ends there. So if it is x from 0 to a, then the particle can only reside inside the box. There is no particle outside the box, because it is an infinite potential well problem. So the potential is infinity elsewhere, so particle cannot cross that potential and go to the other side. but it will remain inside always. So the wave functions, everything for the particle will be confined between 0 to a. So obviously the function will be going to 0 or touching this x-axis at these two edges 0 and a. But if there are further other points which are not these 2 points, and but still the wave function is going to 0 at those points, then we'll say that those are the nodes of the wave function. Say for example, for n equal to 1 you have a sinusoidal wave function sin pi x by a for n equal to 1. So you have no cutting in between. So there are number of nodes is 0 for this case. But for n equal to 2, that then it is sin 2 pi x by a. Then the formation of the wave function will be somewhat like this. Okay. So I may not be very accurate in my drawing, but just for the idea, there is a node here in between, because here the wave function touches the x-axis or crosses the wave function crosses the 0 value up to here, which is at a x equal to a by 2. This is for n equal to 2. You can also cross check why this is true, because n equal to 2 means it is the function of sine 2 pi x by a. So at so at x equal to a by 2, the value will be 2 pi into a by 2, 2 pi by a into a by 2. So this is pi by so this is pi, and sine pi is basically you know that sine pi is 0. That means here there will be a node present. So for n equal to 2 you are getting one node. So for n equal to 2, number of node is equal to 1, which is basically 2 minus 1. Similarly, you can check another point and you will be sure that this has a trend, because if you look at the n equal to 3 case, then it is sine 3 pi x by a, right? So then you will see that this will cross the x-axis twice. How to say that? So this is, let's say this. So okay, so then it will be like, let me use a different color. So again, the drawing may not be very accurate and up to scale, but just for the idea that this is a sinusoidal function where it is sine 3 pi x by, because it is n equal to 3. So here you have two nodes, because here it is crossing the x-axis in between the 2 points, right? These are the points you can get those points where this value will be 0, because 3 pi x by a, when this is equal to n pi, then the sign value will be 0. So then pi and pi cancelling out, so the x equal to n a by 3. So n can be 0, then it is one edge of the wave box, which is x equal to 0. N can be 1, then x equal to a by 3, where it also will be 0. So this point is actually a by 3. Then you can have n equal to 2, then you have x equal to 2a by 3, where also the sign function will be 0. So this point is actually 2a by 3. And finally for n equal to 3, you have x equal to 3a by 3, which is a, which is this other edge of the box. So like that, for n equal to 3 you are getting two nodes, right? So n equal to 3, the number of nodes equal to 2, which is basically 3 minus 1. So that justifies this point that for psi n you will have n minus 1 number of nodes, which is actually you are verifying for the other, for taking up some particular values of n and looking at the nature of the wave function. So this problem is solved. Now the question number 2 is, so this a and b are the correct option for question number 1. Then we go to question number 2. It is saying that the wave function for a free particle of mass m is this. Then a is the normalization constant. Then what will be the probability current? So this thing is already has a formula. You probably already know that there is a formula for probability current or probability density current. So probability current density, when you integrate it, you will get probability current, right? So the formula is, let's say the probability current formula equal to that you define by j equal to I h cut by twice m, then psi del psi star del x minus psi star del psi del x. There psi equal to a e to the power of I kx minus et I h cut. So del psi del x you can calculate. This is aik e to the power of I kx minus et by h cut. Again psi star is simply a e to the power of minus I kx minus et by h cut. So del psi star del x equal to minus I a k e to the power of minus I kx minus et by h cut. So here you get that your j equal to I h cut by twice m. Then psi del psi star del x is basically so this minus I will be multiplied. So minus I a whole mod square e to the power of 0, because this plus I and minus I, so they cancels out. And then psi star del psi del x is again mod a squared plus I k e to the power of 0. So what you are left with is I h cut by twice m a whole mod square into minus 2I k. So you have I into I, which is I squared minus 1, which absorbs this minus 1, taking it a plus 1. So this is h cut k by twice m a whole mod square. Sorry, this 2 also cancels out, so this is not, there is no 2 here. So this is your final answer of probability current. So let us cross check that h cut k by m whole mod square. So this is this. So question number C, option number C is the correct option. Now question number 3 is the function psi equal to sin k1x, sin k2y, sin k3z is an eigenfunction of the Laplacian operator delta squared, which you have to show or prove. So let us prove that if your operator is delta square, which is a Laplacian operator, and it is operating on a psi xyz in 3D it is given. So the Laplacian operator formed in 3D is del 2 del x2 plus del 2 del y2 plus del 2 del z2 acting on sin k1x, sin k2y, sin k3z. Okay, so this is equal to, if you take double derivative, so only the x part will contribute for d2 dx2. So this is k1 squared sin to cos, and again cos to minus sin, so this is minus k1 squared sin k1x. Similarly, for the rest other terms you will also get similar things. So but the sin k2y and k2z will remain unchanged, because of this derivative with respect to x will not affect those. So those part will remain there. Then for the second term, when you take the derivative with respect to y twice, so then you will get minus k2 squared from this term, and all the other two terms remain intact. So this, let's say this whole thing is our psi xyz, right? So you can get back the whole psi, and similar thing happens for derivative with respect to z as well. So you are finally getting minus k1 squared plus k2 squared plus k3 squared into psi. Okay, so if you compare, so you get delta square psi equal to this. This is like an eigenvalue equation where delta square has an eigenfunction as psi. Okay, and the eigenvalue for delta square on psi is this. So you are seeing that this statement is true, that it is an eigenfunction, right? So question number 4 is, this is a Dirac delta potential problem, but instead of a one Dirac delta, it has two Dirac delta. That's a double delta potential function, where this representation of the potential function is like this. Okay, so and g and a are positive constants. Now the general form of the bound state odd wave functions when the energy E is less than 0 are what? So this can be a pretty elaborate solution, but I will not go into much detail or elaborated derivation, because you should be already familiar with a single delta potential problem. So instead of a single delta, you just extend it to double delta and check out the wave functions, and then out of those you apply the boundary conditions, you get to the final wave functions, and then you choose what will be the odd wave function for this bound state. So this is all we have to do. So let us start. Like, first, for any kind of problem like this, you start with drawing the potential. So in this case, the double delta potential you have to draw. So which is basically, if you have axis like this is x-axis, and this is y-axis vertically, this is x. So x equal to plus a and minus a. So this is 0. This is x equal to plus a, x equal to minus a. So your function will look like this, and then a sharp Dirac delta potential. Okay. Then again 0. again a sharp dirac delta potential. This height of the potential is given by this factor g, other constant. So this is your Vx. So Vx equal to minus g. So this is negative side. So this is kind of a extent is negative side. That is why, because it has minus g. So minus g delta x minus a plus delta x plus a. So out of these three, you can divide into three regimes. Regime 1 is here, x less than minus a. Then regime 2 is the whole regime between x to minus a to plus a. And then regime 3 is all over x greater than plus a. So you have three regimes you can identify based on the potential distribution. So regime 1 is where you have x is less than equal to minus a. 2 is where minus a to plus a. And 3 is greater than equal to a. Okay. So now you have, for each of them you can solve the Schrodinger equation and get the wave function form. So I will not show everything, but because it is already known. So let's say for regime 1, if you take the wave function as psi 1, then your Schrodinger equation is minus h cut square by twice m del 2 psi 1 del x2 plus v psi 1. V will be 0 here because the potential everywhere else except for the Dirac delta point will be 0. So this is 0 equal to e psi 1. So you are getting d2 psi 1 dx2 equal to minus 2me by h cut square psi 1. Now because it is said that it is bound state, that means e less than 0, because that is the criteria for a bound state. So if E is negative, then this 2me by h cut square is a positive quantity, so that you define as a square term of k squared, because k square has to be greater than 0, and because there is a negative sign already with E less than 0, so this takes care of this whole positive thing. So now this kind of a solution equation will give rise to forms like a to the power of sorry so a to the power kx plus b to the power of minus kx. Now on this solution you have to apply the physical reasonability or the normalization condition of the wave function, because it is in the zone where x is negative, because x is less than equal to minus a, that means x is negative. In this zone, if you extend up to infinity, which is to the negative side, extends to minus infinity, the wave function should not diverge if it is a physically realizable wave function. But in this wave functional form, you see that the second term for x tends to minus infinity, you see that b e to the power of minus kx goes to b e to the power of minus and minus plus infinity, which is diverging. So this is incorrect because that is not physically true or correct. So the b term has should be avoided here. B should be plugged into as 0. Rather than that, you have to take only with the go with the first term, which is exponentially increasing towards positive x. That is because on this term, if you put the limit of x tends to minus infinity, this term will go to 0, because then e to the power minus infinity is 0. So that is true physically. This is physically invalid. So by this condition of normalizability, you have psi 1x equal to a to the power of plus kx. Now similarly for regime 2, if you apply the Schrodinger equation, here you see that again the potential is 0, and you'll be having the psi 2x as both the combination of c to the power of plus kx plus d to the power of minus kx. And because it is a bound regime, there is no extends to plus minus infinity limit here. So both of the terms we can exist together, and none of the term will cause the wave function to diverge. So that is why we keep both terms. Now for the regime 3, again you are on the other limit. So here you have, let's say the wave function psi 3 here is a p to the power of kx plus g e to the power of minus kx. Now here x is greater than 0. So x tends to plus infinity, which part will diverge? So you'll see that this part diverges, right? So this part you have to plug to 0. So you are only left with g e to the power of minus kx. So out of these calculations, if you just write down now the wave function finally, so this is c to the power kx plus d to the power of minus kx, and psi 3x equal to g e to the power of minus kx. So this is the three regime wave functions. Now we still have not applied the boundary conditions. After applying the boundary condition, you can find a relation between A, C, D and G. So the boundary conditions you need to apply are, boundary conditions are simple, that the wave function psi x is continuous everywhere, and the derivative, second condition will be the derivative of the wave function will be like discontinuous only where the potential diverges. So these are the two boundary conditions. So the first one is that psi is continuous everywhere. That means if you take psi 1 at x equal to minus a, it will be equal to the other side, which is psi 2 at x equal to minus a. Okay, this is one condition. So you can apply it like, so you put psi 1, that means here, so a to the power of minus ka equal to psi 2 is c to the power of minus ka plus d to the power of plus ka. Okay, so this is, let's say, equation number 1 from this boundary condition. Then similarly, the other point, which is plus a, you see that psi 2 at x equal to plus a will be to the other side regime, which is psi 3 at x equal to plus a. So from here we will get that c to the power of k plus d to the power of minus k will be equal to g to the power of minus k, which is your condition number 2 or equation number 2. Then the discontinuity of the del psi del x will give rise to the third condition, which is basically saying that your this you can check out from the Dirac delta function potential. How did you solve it for a single Dirac delta potential? So I'm not going to write down everything in detail, but just for the idea, here you will be having different equation like del psi del x at minus a plus epsilon, which is basically the other side of minus a, that means this is psi 2 regime, right? And minus to the left side, that is psi 1 regime, so this is minus a minus epsilon. This difference is minus this difference is 2m by h cut square, minus a minus epsilon to minus a plus epsilon. Then the potential is minus g delta x minus a plus delta x plus a psi x dx, right? So this is equal to, if you now know the Dirac delta function properties, you will know that for minus a, around minus a, you are taking a very small limit because this epsilon is actually tending to 0. So in this limit you will only have survived only this term, which is delta x plus a, which will give you basically minus g psi, this will be psi 1, so psi 1 of minus a. Okay, so from here, if you take the equation or take the expression of psi 2 and psi 1, take the derivative and put all these values of x, then you will find out that you will be having a term or equation like a e to the power of minus k 1 minus 2 mg by h cut square k equal to c e to the power of minus k uh, minus d e to the power of plus k, which will be your equation number 3. Okay, so and similarly for the last part, the boundary condition on the discontinuity of the wave function at the Dirac delta potential at x equal to plus a, will be again having psi 3 del psi 3 del x at x equal to plus a plus epsilon minus del psi 2 del x at x equal to a minus epsilon equal to 2m by h cut square a minus epsilon থেকে to a plus epsilon minus g delta x minus a plus delta x plus a psi x dx. There psi 1, psi 3. So from here you can simplify and write the expression as f e to the power of minus k 1 minus 2mg divided by h cut squared k equal to d e to the power of minus k minus c to the power of k. So this will be your equation number 4. Now you can deal with 1 plus 3, which is basically 3 is this, 1 is this. So then we will be having a simplified form of in terms of a and c, where you can express a and c in a relation, which is a into 1 minus mg by h cut squared k equal to c, which is equation number 5. And similarly for 2 plus 4 you will be getting g into, sorry, this will not f, this will be g into 1 minus mg by h cut squared k equal to d, which is equation number 6. So out of all these equations, finally you can use this c and d 5 and 6 in 1, which had c and d on the right hand side, which is this term. So you can replace c and d by this. So then you will be getting a form a equal to f e to the power of 2ka h cut square, sorry, not f again but g. So h cut square k by mg minus 1. So this is equation number 7. And similarly, if you use 5 and 6 in plug in 2, then you will get g equal to a e to the power of 2ka h cut squared k by mg minus 1, which is equation number 8. Now if you take equation 7 by g, so that is equal to a by g equal to e to the power of 2ka h cut square k by mg minus 1. And if you have 8 by g, you have g 8 by a basically. So this is g by a equal to e to the power of 2ka h cut square k by mg minus 1. So from out of these two, you can see that the right hand side is exactly same. That means your a by g equal to g by a, or g squared equal to a squared. So the only solution that it is possible for satisfying this is g equal to plus minus a. So two possibilities are there. So now based on the question they have asked you is the bound state solution of wave function for the odd wave function that you have been asked. So you'll see that if you plug in g equal to minus a, then only you will get a odd wave function, but if you plug in g equal to plus a, you will get a even wave function. So let us put g equal to minus a, then the psi 1x remains as it is, that is a e to the power of minus kx. Psi 2x, that we also like we are not writing down in the details here, but you will later on find out that your c is equal to basically will be d. So it will be having a form like and finally psi 3x that had g e to the power of plus kx. So instead of g we will put minus a e to the power of plus kx. Now here this is for wave function to be odd, psi to be odd, it has to satisfy psi some value, let's say minus b equal to minus of psi b, then we will say that this is odd. So psi minus b, that means it is in the zone of x less than 0 or in the 1 regime. So we'll put a to the power of minus k minus b, which is equal to minus of psi b, which is this regime. So this is minus of minus a to the power of kb. That means you are getting a to the power plus kb equal to a to the power plus kb. So this is satisfying that this is an odd wave function. But if you had put g equal to plus a, then psi 3x would have become a to the power of plus kx. Then your psi minus b will not be minus psi b, but it will be equal to psi b. So then it is even wave function. That means for the answer at that you have to give here is for the odd wave function case. So for bound state odd wave function, this Dirac delta potential has a solution like this. Okay, this you can simplify further, that this is a cos hyperbolic kx form. So this is, you can see this is 2 c cos hyperbolic x. This 2c you can rename by something else. Let's say you call as b cos hyperbolic x. But this a to the power minus kx for x less than minus a, and this is x greater than a, and this is between greater than equal to basically this range. So now you look at the solution answer options. So there is a little typing mistake here probably, because it is matching with our answer for this case, but here a to the power of minus kx for uh, okay, so not this, but you are getting for x less than minus a, you are getting a to the power of uh, plus kx, I think. So I think I have written it down. Yeah, a to the power of plus kx. Sorry, I have by mistake, this should be plus and this should be minus. Okay, so now for x greater than a, it is a to the power of uh, minus kx, and for x less than a, it will be minus a to the power of plus kx. So this is not a, basically this will be minus a, but this is the correct answer. So that we have derived. Now question number 5 is that a spin-half particle in the state half uh, plus minus, then the expectation value of the operator I sx x sy will be how much? Sorry, I skipped one question. So question number 5 is spin 1 particle in the basis in the state psi of this in sz basis, then sx expectation value is what? So let us go here. Question number 5 is your psi equal to 1 by root over 14. So this is already normalized. So this is 1 by root over 14 is the normalization prefactor. Okay, so this is the state in sz basis. So also this is a spin 1 particle, that means you have to deal with 3 cross 1 vectors or 3 cross 3 matrices instead of 2 cross 2. So because this is s equal to 1. Now then sz basis, so sz basis vectors are simple, that 1 0 0 0 1 0 0 0 1. So these are the sz basis. This is the most standard basis. But then the a6 is another operator that is along x, but that has not the same basis as sz. So how you can represent the a6 matrix form in terms of this sz basis vectors? So the idea is that your s plus ladder operator or with plus sign is a6 plus isy is minus equal to sx minus isy. So 2sx equal to basically s plus s minus. So your sx cap is simply because basically s plus s minus by 2. Okay. So then if that is the case, then you already know that s plus, how that operates on a state Sm. So this is basically, there is a form that root over s into s plus 1 minus m into m plus 1 each cut, and the state goes to s m plus 1. Similarly, if s minus operate on Sm, then it will be having instead of plus, there will be a minus sign and there will be a minus sign here. So by this, you will see that if your a is equal to 1 fixed in the question, then m can go from minus s to plus n gaps of 1. So it can be minus 1, 0 and plus 1. So then the states can be such that, so let's say because a is equal to 1 is fixed, we are only representing the state as m, which is 1, 0 and minus 1. So your s plus 1 plus 1 will be 0, that you can check from here. I am not deriving it again because similar sort of a problem with the angular momentum case J was done earlier in some earlier week's assignment. So the idea is simple and similar, just instead of J you have S now. So J and MJ, instead of that you have now S and M. So s plus on 0 will be h cut root over 2 1, and s plus on minus 1 will be h cut root over 2 0. Similarly, s minus on 1 will be h cut root over 2 0. S minus 0 will be h cut root over 2 minus 1, and s minus 1 will be 0. So you are having all these things. Now you can write down what is Sx, S plus operator in this basis, M basis, right? So then you have M and M here. So this is minus 1, 0, plus 1. And this is, or plus 1, 0, minus 1 as well. And this is 1, 0, minus 1. So the terms will be like M, where M is 1, is plus 1. The second term will be 1 is plus 0. Third term will be 1 is plus minus 1. Then this term will be 0 is plus 1. And similarly all the other terms has to be filled up for this matrix. So the matrix elements are defined like this. Now since you already know these, you know that like s plus on 1 will be 0. So 0 with 1 they are orthogonal, so that will give rise to 0. But on the second term you have s plus on 0 is h cut root over 2 1. So this is h cut root over 2 1 1, right? So okay, so that is there. So you have this is equal to a non-zero value because this is normalized, this is 1. Similarly for the rest of all the other terms you can find out, and the final form will be, I'm directly writing the form 0 0, sorry not here 0, so you can take the h cut as common, and then you have 0 root over 2 0 0 0 root over 2 0 0 0. This is S plus matrix in the SZ basis. Similarly, you can do the same thing for S minus at matrix. Instead of S plus, you will be having to use this kind of form, but rest of the things will be similar. So I'm directly writing down the form in SZ basis will be H cut 0 0 0 root over 2 0 0 0 root over 2 0. So once you have that, you know that your Sx is nothing but S plus S minus by 2, which is basically h cut by 2 0 root over 2 0 root over 2 0 root over 2 0 root over 2 0. So if you take root over 2 common, you see that this is h cut by root over 2 0 1 0 1 0 1 0 1 0. This is all in the SZ basis. Now once you have that, now it is simple to take the expectation value, that which is basically your psi was given as 1 by root over 2 plus, sorry not there, the psi was given as 1 by root over 14. So 1 by root over 14 is on both terms, so it will be squared. So then psi kate will be having a complex conjugation, so it will be having 1 2 minus 3i, because this is a psi kate psi bra. So there will be a complex conjugation psi sign over here. Okay, and then you have 0 1 0 1 0 1 0 1 0, and you have 1 2 3 I. Thus you get, if you solve this term by term, you will get a value answer of h car root over 2 by 7. So this is your final answer. So let us cross check the options. This we are getting. This is also the correct answer. Now question 6 is, a spin half particle is in the state 1 by root over 2 half plus plus minus. So this is basically the state. This is basically the eigenstate of the Sx operator, right? So because this kind of form comes there, and then the expectation value of the operator I Sx Sy will be what? So this is a spin half particle is equal to half. That means here you will have to deal with only 2 cross 2 matrices like that. So 2 cross 2 spin matrix will be there. So you know that Sx equal to h cut by 2 sigma x in terms of Pauli spin matrix, Sy equal to h cut by 2 sigma y. So I Sx Sy will be I h cut squared by 4 sigma x sigma y. Now you know the form or the property of Pauli spin matrices, that sigma I sigma z equal sigma x sigma y equal to I sigma z. So this is I h cut squared by 4 into I sigma z, which is minus h cut squared by 4 sigma z. Okay, so if that is the case, then you have I h cut squared by 4 sigma z. In the expectation value, you have to take with respect to the state 1 by root over 2 plus minus. So this is basically in matrix form. You can write down 1 0 0 minus 1. Now for the expectation value, you also have to look at the state. So state, this is 1 by root over 2. So this is in Sx basis. This case state can be represented like this in a vector form. So once you have to take the expectation value of I Sx Sy, this is psi I Sx Sy psi, which is basically 1 by root 2 whole squared, then 1 1, then minus h cut squared by 4, 1 0 0 minus 1, and then 1 and 1. So like that, if you do minus h cut squared by 4 into half, 1 1, this is 1 plus 0 0 minus 1, this is minus h cut squared by 8, 1 1 1 minus 1, minus h cut squared by 8, 1, this is 0. So final answer you are getting as 0. So this expectation value is 0. Now question number 7. Consider a system of 5 non-interacting particles with identical spin that are in the same state half half. So confined to move in a one-dimensional potential well of length L. Then the potential Vx equal to 0 for x from 0 to L and the infinite elsewhere. Then the ground state energy of the system will be this, where n value is what? So first of all, this is a 1D particle in a box problem. But the twist is that you have now, instead of one particle, you are dealing with 5 particles which are non-interacting with each other. So they will behave like independent of each other. Their energy values will be independent and the total energy will be a sum of the individual particles energy. So that is why they are that is the significance of being non-interacting. Now also thing is that they are all identical particles, right? So and you see that they are in the same state of half half. So half means this is s comma s. So s equal to half means they have a half integer spin. So this means that they are fermionic particles, identical particles which have the spin as half integer multiple. So that will be fermionic. That means in each state there can be at max one particle. So that means that from here you know that if there are five particles, they will be occupying five different states altogether. They will not be in the same state anymore. So then, respecting that, you have the potential, infinite potential, or the particle in a box kind of a solution of energy, E1, E2, E3, E4, E5. So starting from the ground state, which is E1, the particles start filling up, and the five particles will be occupying five different states up to E5. And you know that En is basically n squared pi square h cut squared by 2m l squared. That means all are non-interacting particles. So the net energy for all these particle system is E net equal to sum over Ei, where I goes from 1 to 5. Okay, so here you can write down the constant as common, n square pi square h cut squared by 2m l squared. Then for n equal to 1, this 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. You will see this will come out as 555 pi square h cut squared by 2m l squared. So your value will be 55. Now question 8 is, for the Hamiltonian like this, h equal to a 1 2 and then 2 1. So this is kind of a projection operator sort of a thing. Now obtain the state vector for t greater than 0, then the corresponding probability for it to be in the state 2 will be what? So you have to obtain the state for t greater than 0. So you have to start with some psi at t equal to 0, and for t greater than 0 you have to time evolve. So you have to apply the time evolution operator, which is related to the Hamiltonian operator, that you will see. And after that you have to take the probability for the state at being at 2. So let us choose a page. So first of all, the Hamiltonian is a, that means Hamiltonian form will be 0 1 1 0. Why? Because this part is, so this is 1, this is, if this 1 and 2 are the basis vectors, I assume, then this will be like this. So the first term will be 1 h1 1 h2 2 h1 2 h2. So 1 h1 is basically like this term. Let's say this is 1 a, this is already 0 because they are orthogonal to each other, so that is why 0. The second term is 1 a, so this is like, okay, 1, then h is 2 plus 1 a, this time will be 0, this will be 1. So this is 1 a 1, which is basically a into 1, which is a. Then here the second term would have been 1. So this part is 1, but anyway this will give you a is a constant, so 1 and 2 again, this is 0. So you will see that eventually you will get this kind of a form, that you will left with 0 1 1 0. This is your Hamiltonian form. Now you have to take a time evolution operator, which is u. U t is a time evolution operator, which is nothing but e to the power of minus I h cap t, which is like e to the power of minus I a sigma x t. Why I am writing down like this? Because this is, identify this, this is as I sigma x matrix. So this is a sigma x. So this you can in term other terms write down as I a okay. So this kind of a form is familiar to you because again this is solved in a previous assignment, that if you have a form given like this, then if you expand the exponential form and in a power series, and if you separate out the odd series and the even series, you will get from odd even series you are getting the, from the odd series, yeah, from the even series you will be getting the cos series, and from the odd series expansion you will get the sine series. So that will be equal to I cos at. Okay, so then you have cos and sine terms coming from here. Okay, so here theta equal to 80 in this case. So then if you say 1 is your initial state, so psi 0 equal to 1 equal to 1 0, then what will be psi t for t greater than 0? That will be simply time evolution operator operating on psi 0, which is time term is also with a sigma x form, so this is 0 1 1 0, and then with 1 you have the state as 1 0. So what you are getting is cos 80 times I minus sine I 80 . Okay, so this you can identify that this is cos 80 1. This state is basically the 2 state because this is the another basis state sin 80 2. Okay, so now the probability of finding it in the state 2 will be this whole mod squared, which is I squared is equal to, this is whole mod squared. So I squared is also plus 1 from the modulus sin squared 80. So you are getting the answer as sin square 80 as the correct answer. Then you have 9. The wave function of a system in cylindrical coordinate is given by this. Okay, and A is a real positive constant. What is the most probable value of rho? So you know for cylindrical coordinate the volume element is rho d rho d phi dz. So if this is the volume element, then the most probable value will be where the probability is maximum, right? So then the probability is psi whole mod square dv equal to this is a to the power minus rho by a, and from dv you have rho d rho d phi dz. Now rho will be going from some 0 to rho naught, but the other terms like d phi dz phi equal to 0 to pi and z equal to from minus z to plus z, so this term will not contribute in rho because they are independent of rho. So the only radial part or a rho dependent term is rho from 0 to um, infinity, not rho naught but infinity. Say whole mod square to the power minus uh, 2a by rho. Basically, if this is squared, this is also be squared into rho d rho phi dz. So the only part with rho is this. So for this to be maximum, then a whole mod squared minus 2 by a to the power of here you get that sorry, I have not taken the derivative properly. So the probability of this thing has only rho dependence on a whole mod squared to the power rho e to the power of minus 2 rho by a. Okay, so for it to be maximum, this is 1 e to the power of minus 2 rho by a plus rho minus 2 by a e to the power of minus 2 rho by a equal to 0. So this is e to the power minus 2 rho by a 1 minus 2 rho by a equal to 0. So the two options, simple option is 1 by 2 rho by a equal to 0. So rho equal to a by 2. So where this will be maximum. So we are getting a rho equal to a by 2, but somehow this is not given as the correct answer. So I think there is a mistake in choosing the answer here. The answer should be a by 2 and not a. A will be a correct answer if instead of cylindrical coordinate you are given a spherical coordinate system. Okay. So now the last question is, if psi and phi belong to the same vector space, then the outer product is another vector. That is false because such kind of an outer product is not a vector but a matrix form that we saw. That if this kind of a form is outer product, that is called, but it is actually a matrix, not a vector. So with this we have solved all 10 questions on this week 12.